Okay, I think it's about time. So, good morning, good afternoon, good evening, everyone. Welcome to today's second paper presenting sessions. And for this session, we will have four presenters. And the first one is Yuichiro Okashita, and he will going to present his work mastering Othello with genetic algorithm and reinforcement learning. Okay, please start your presentations.
Thank you. Hello everyone. I'm Yuichiro Okashita from Hosei University. Today I'm going to present our paper titled Mastering Othello with Genetic Algorithms and Reinforcement Learning. This is joint work with Yuichi Sudo, also from Hosei University. Now let's look at the outline for this presentation. First, I will discuss the motivation to our research. Then I will introduce the background and related work. After that, I will explain our proposed method. Finally, I will present our experimental results. Othello, also known as Reversi, is a two-player strategy game played on an 8x8 board. This game was weakly solved by Takizawa in 2023. His work showed that a game between two optimal players will always result in a draw. And if the game is already solved, is there any value in developing strong AI for it? Let's think about weakly solved actually means. In a weakly solved game, the optimal sequence of moves and the final outcome are known, but only from the initial position. Therefore, to find optimal moves for arbitrary positions, a strong AI is still needed. And historically, the evaluation function in Othello was built on classical machine learning techniques. Logistero, which greatly influenced modern Othello programs, employs local disk configurations as features and calculates their weights using linear regression. And here are the actual patterns used in Logistero. As you can see, they include horizontal and vertical lines and various patterns around the corners and edges, which are strategically important areas in Othello. On the other hand, several studies have employed deep neural networks as the evaluation function for Othello. The most successful example is Oliver. It uses a simplified version of AlphaZero and was trained on 19 cloud computers for 1 month. Now let's compare the two approaches, classical machine learning and deep learning. Classical machine learning typically requires careful feature engineering due to its limited representational capacity. Deep learning, on the other hand, can learn directly from the board state without manual feature engineering. However, deep learning is much more computationally expensive. Therefore, in some games, a classical machine learning approach can actually be stronger. This is because its computational efficiency allows for a much faster and deeper search. The feature engineering in classical machine learning is fundamentally reliant on domain-specific knowledge, which requires deep expertise in the game's strategy. This led us to ask, what if we could automate this feature engineering process? If we could, we might be able to develop a computationally efficient evaluation function without such expert knowledge. This is the core motivation for our research. Our proposed method uses classical machine learning but does not require any manual feature engineering. Instead, its representational capacity is enhanced through automated feature engineering. This is the overview of our method. Our method has two main stages. First, we perform automated feature engineering. We use a genetic algorithm to optimize the shapes and combination of n-tuple. I will explain what n-tuples are in more detail shortly. Second, once the features are engineered, we use MCTS-based self-play reinforcement learning to learn their optimal weights. Now let's go over the background and related work. Let's begin with the state value function, Vs. In our context, it maps a board position to an expected outcome. We use it to represent the expected win rate with draws counted as 0.5 wins. To align with the standard terminology in reinforcement learning, we will use the term value function instead of evaluation function from this point forward. Next, I'd like to discuss n-tuple systems, which are a core component of our work. The n-tuple system is a feature extraction method originally developed for the field of character recognition. It was later adapted by Lucas for use in games' value functions. So let's take a closer look at what an n-tuple is. Formally, an n-tuple is defined as a sequence of coordinates for n cells on the board. For instance, the 4-tuple highlighted here is composed of 4 cells, C4, D4, E4, and F4. Here is another example. This 3-tuple is composed of 3 cells, A1, B1, and A2. When evaluating positions, we use k instances of n-tuples. Each n-tuple has 3 to the n possible features because each cell has 3 states, black, white, and empty. So you can represent the presence or absence of each n-tuple's feature using a k times 3 to the n dimensional vector called the feature vector, phi s. Similarly, we can introduce a weight vector, theta, whose dimensionality is the same as the feature vector. Each component of theta represents the weight of a corresponding feature. In addition, we add an extra component to both vectors to represent a bias term. Finally, we model the value function by the dot product between the weight vector and the feature vector, and then apply a sigmoid function to represent the expected win rate. The components of weight vector are the parameters of the value function, which are optimized by gradient descent. As a point of reference, the logistical params we discussed earlier can be regarded as a form of n-tuples. The crucial difference, however, is that those params were handcrafted. In contrast, our approach is to generate the n-tuples automatically. Now let's move on to the related work. I'll summarize the 3 main studies that informed our approach. First, there is a general game learning method using n-tuples generated by a random walk. While this approach is domain independent, its search for effective n-tuple is not efficient. The second work employs an evolutionary approach. However, its search for n-tuple shapes is inefficient, as new shapes are introduced only through the low probability mutation phase. Due to time constraints, I will now focus on this third study by Kramitz et al., as it's the most relevant to our own work. Kramitz et al. Proposed an n-tuple optimization method using a genetic algorithm variant known as BRKGA. A key idea in their method is to encode all k n-tuple shapes into a single real-valued vector. This representation allows n-tuple shapes to be altered not just during mutation, but also directly during the crossover phase, enabling a more powerful search for new shapes. However, for their fitness function, they measure how accurately the n-tuples can predict game outcomes using existing game records. The major drawback here is that this approach is no longer domain independent. It relies on having access to a domain-specific dataset of games. With this context in mind, let's turn to our method. For the n-tuple optimization, our method also utilized BRKGA, similar to the work of Kramitz et al. However, we introduced 2 main modifications. The first is a new solution decoder. I will explain the role of this decoder in more detail in just a moment. The second is self-play data generation, which is intended to make our method domain independent. Okay, let's take a closer look at how BRKGA works. First, BRKGA stands for Biased Random Key Genetic Algorithm. The key feature of BRKGA is how it represents a solution. Each individual is encoded as a real-valued vector. This vector itself is not the solution. Instead, the procedure called the decoder is used to convert the real-valued vector back into a solution during individual evaluation. In the context of our work, a solution corresponds to the k instances of n-tuples. Kramitz et al. Proposed the decoder for n-tuple generation. Due to time constraints, I will not explain the details of their decoder. However, their decoder has a key drawback. It can form spatially disconnected n-tuples. For instance, as you can see, a disconnected 4-tuple can be formed. To tackle this problem, we introduce a new decoder. In our decoder, the encoding is the same as in Kramitz et al. A single n-tuple is represented as a real-valued vector, where each component corresponds to a cell on the board. However, the way cells are selected is different. Our decoder selects the next cell from the cells adjacent to the already formed I-tuple, choosing the one with the smallest value. Let's look at the concrete example. Here is the 64-dimensional vector arranged as an 8x8 grid. First, our decoder selects the minimal value from this vector and creates a 1-tuple from the corresponding cell. The next step is to scan the adjacent component around this 1-tuple. Then, it selects the minimal value from this component to form the 2-tuple. Similarly, the decoder then scans the cells adjacent to this 2-tuple and selects the minimal value from them to form the 3-tuple. This iterative process continues until the complete n-tuple is formed. In this particular example, the selection process is repeated until the 5-tuple is formed. Up to this point, we've focused on encoding a single n-tuple. In our actual implementation, however, we encode all k instances of n-tuple into one large vector. This vector is composed of k segments, where each 64-component segment corresponds to the cells on the board, as described before. During individual evaluation, a decoder is then applied to each of these k segments. Now let's walk through the individual evaluation process in our work. First, for each individual, we decode its vector to get the k instances of n-tuples. These are used to construct the value function vs theta. Second, we optimize the weights of this function theta using gradient descent with data generated from self-play. The objective here is to minimize the cross-entropy loss between the function's prediction and the actual outcome for the self-play game. Finally, the fitness of the individual is assigned as the reciprocal of that cross-entropy loss. So let's now look at exactly how this self-play data is generated. In BRKGA, the population is divided into two groups, elites and non-elites. Elite individuals have the top PE fitness, where PE is a hyperparameter of BRKGA. Due to time constraints again, I will not explain the generation alternation model in BRKGA and will focus on self-play generation. We generate the self-play data using only the elite individuals from the population. First, we create value functions from the n-tuples of the elite individuals. Second, we initialize the weights of these value functions using the TD lambda method. Third, we select two of these value functions uniformly at random to play a single game. This game is guided by an MCTS with 3,200 simulations that uses the selected value function for evaluation, and the resulting game record is saved. This entire self-play process is repeated until the desired number of game records has been generated. This diagram summarizes the entire n-tuple optimization process that we've discussed so far. It consists of two main components, the GA module on the left and the self-play data generation process on the right. Finally, I will explain the last stage of our work, which is self-play reinforcement learning using MCTS. After the n-tuple optimization process, we have a high-quality value function with an optimized n-tuple structure. The final step is to further refine its weights to maximize performance. The reinforcement learning process itself is similar to the one used in AlphaZero. It's an iterative loop consisting of two stages. First, we generate self-play data by playing games using MCTS. Next, we train the value function's weights on this data using gradient descent. This cycle of self-play and training is repeated several times to continually improve the policy. So now let's move on to the experimental results to see how our method performs. In our experiment, we optimized 12 instances of 10 tuples. The process was run for 300 generations. Here are the final n tuples our method discovered. As you can see, they are concentrated around the corners and edges. These areas are known to be strategically important in Othello. Now let's look at the self-play reinforcement learning experiment. In this phase, we took the value function with our optimized n tuples and trained its weights on self-play data. This self-plate was guided by an MCTS with 800 simulations per move. The training was conducted over 10 cycles. In each cycle, we generated 500,000 self-play games, leading to a total of 5 million games played throughout the entire process. And so let's evaluate our agent's final strengths. In our experiment, the agent's strength was measured in a match against EDAX, one of the strongest Othello program available. We used 500 initial positions selected uniformly at random from the XOT small list, which is a dataset of balanced positions. For each position, 2 games were played with the colors swapped, for a total of 1,000 games. Draws were counted as 0.5 wins. This figure shows the win rate of our proposed method against EDAX. For this experiment, our agent used an alphabet search with its search depth set to the same level as EDAX. As the figure clearly shows, our agent maintains a win rate of over 50% against all tested levels of EDAX. This is comparison to previous work. However, due to time constraints, I leave it for Q&A. The codes for our experiments is available on GitHub under the MIT license. This is conclusion and future work. That concludes my presentation. Thank you for your attention.
Okay, thanks for the very interesting presentations. Is there anyone has questions for the presenter? Okay. And okay, currently I don't see any question from the QA region. So let me ask one. So those n-tuples are generated by your genetic algorithm process. So it looks like we cannot ensure which region and how many tuple will be selected during your. Of course, we can control the number of tuple, but it looks like we cannot control the corresponding region chosen by your genetic algorithm. But we also know that in Othello, the region is quite important. So if it's possible to consider the exact location on the game board rather than randomly uniformly distributed all the n-tuple, do you think it's meaningful, or do you think the current random uniform solution is already quite good?
Sorry. Could you
Yeah,
rephrase
I
it?
think probably is too long. I mean, for your n-tuple, can you show the slide n-tuple for me?
Yeah.
Since those are get from the genetic algorithms result, but do you think we should put more attention on some of the specific location, and or for now you think the current result is already quite good?
Okay. Honestly, I don't think these n tuples are best for Othello, because in EDAX and Logicero uses the sequential line patterns, but these n tuples, there is there is few sequential line patterns in these n tuples. So yeah, so we should improve more diversity of individuals during genetic algorithm, because in my experiment, the diversity of individuals rapidly decrease in within 300 generations.
Okay. So it look like you need more training or more experiment to improve the result, right?
Yes,
Okay. Thank you.
thank you.
If there is no further questions, then we thank the speaker again, and we will go to the next presentations. So for the okay, you can end your screen sharing now. Okay, thank you. So for the second presenter, let's welcome Karen Murakami, and she's going to present the paper with title with static and intrinsic diverse in Go agents. Let's welcome the speaker.
Can you see my?
Yeah, we can see your slide, and we can also hear you.
Thank you. Can I start?
Yes, please.
Thank you. Thank you for attending my presentation. The title of my talk is Static and Intrinsic Diversity in Go Agent. My name is Karen Murakami. Here is the overview of this presentation. The theme of this research is a game of Go, which is a territory capturing board game. In recent years, Go AI has become much stronger than human players. In addition, powerful Go AIs are accessible to both professional and amateurs today. As a result, the focus is shifting from sheer playing strength to usability. In this paper, our goal is to develop a Go AI agent that can present multiple strategies rather than only one. Another main theme of our research is clarity diversity. Here, we briefly describe the notion of diversity in AI. For example, people may think, I want to work with an AI that feels compatible with me, or I want ideas that match my preferences, or on the contrary, I want to get ideas that broaden my perspective. Therefore, diversity in AIs can increase the value of AI in practical use. For this reason, we aim to develop a Go AI that can propose not only multiple but diverse strategies. In addition to diversity, it is important to maintain the clarity of AI. In other words, we want not only diverse AIs, but also AIs with high quality. In Go AI, clarity is corresponds to playing strength. Ideally, each strategy should be different while having similar strengths. This is a concept of clarity diversity, which combines both aspects. Our baseline is AlphaZero, which was derived from AlphaGo. It also served as a basis for subsequent models, such as Gamble AlphaZero and Katago. AlphaZero is a specialized AI with very high playing strength, surpassing humans and large language model-based approaches at this moment. It is based on deep reinforcement learning, using a neural network. The input to the network consists of the board positions and the players to move. The outputs are the policy and the value. The policy is a matrix that represents the probability of placing a stone at each location. The value is the expected game outcome, indicating which player is more likely to win. Anyway, this model structure means that from a given input, alpha 0 can only provide a single move or a single idea. However, in human collaboration, it is often desirable to obtain multiple ideas. Therefore, to achieve quality diversity in Go AI, we propose two methods. In both methods, multiple agents are trained within a single model. The first is the static method, which characterizes each agent by the area of the board it aims to secure. The second is the intrinsic method, which trains each agent using an intrinsic reward to promote diversity. Next, I will explain these two approaches in detail. First, in static methods, we characterize each agent by the area of the board it aims to secure, which we call the zone. To implement this idea, we added an additional input channel that represents the zone. We also added an output channel which predicts the value for the designated zone. To train the network for the static methods, we use our original metric called region occupancy as training level. Region occupancy is calculated as a ratio of the score at the end of the game within the designated zone. As the score in the zone increases, the region occupancy also increases. For example, suppose we are black and the designated zone is the upper right area of the board. If the endgame position looks like the one in this figure, the region occupancy for black is 0.25. Second, on the other hand, in the intrinsic method, we train each agent using an intrinsic reward that promotes diversity. By training with the intrinsic reward, each agent naturally develops its own characteristics that differ from those of the other agents. When we, when each agent plays Go, the intrinsic reward is used in combination with the extrinsic reward. The extrinsic reward is a reward normally used in reinforcement learning. In the game of Go, the extrinsic reward corresponds to the win or loss outcome. We defined our original feature vector and calculate the intrinsic reward using that. This intrinsic reward measures the novelty of the agent's behavior based on diversity. And diversity is defined using the difference between the average of the feature vectors of each agent. Psi. Diversity consists of two forces. A repulsive force, which encourages agents to behave differently from one another, and an attractive force, which prevents them from becoming too different. To compute that the intrinsic reward, we desire a feature vector that represents the characteristics of each game, or equivalently, each agent strategy. We define the feature vector based on the board positions in the early game and the end of the game. Similar to the static method, in the intrinsic method, we also add an input channel that indicates the agent ID. In addition, we add an output heads that predicts the intrinsic reward value. The experimental results of static methods. This figure illustrates normal game result with a supervised learning model. The x-axis represents learning progress, and the y-axis represents the error rating, which indicates the strength of the agent, and which corresponds to the agent's quality. As the error rating increases, the strength of the agent also increases. And in this experiment, we call our static method agent as the zone RL agent. The zone of the zone RL agent is set null. This means our static method agent in this experiment merely seeks to win the game. As a result, the RL agent orange line baseline surpassed the SL agent on the 200th edge, while the zone RL agent, our method, blue line, nearly caught up with the SL agent around the 400th edge, and its error rating was still growing at 400th edge. Next, these figures illustrate regional game results with a supervised learning model. Similar to the previous graph, the x-axis represents the learning progress. However, the y-axis represents the region occupancy in the intended zone. Like the error rating, as the region occupancy increases, the strength of the agent in the intended zone also increases. There are two figures. The case when the zone is set center, which means our static method agent seeks to prioritize the center part of the board, and the case the zone is set edge. In both cases, the zone RL agent successfully earned region occupancy above 0.5 in the zone set. This indicates that the zone RL agent successfully focused on the intended zone. Next, experimental result of the intrinsic method. This figure shows the experimental result of the intrinsic method. The x-axis represents the average diversity calculated from the play data during the training process, and the y-axis represents the average error rating of agents against a supervised learning model, which corresponds to quality. Here, the parameter L0 denotes the width of the acceptable range of diversity during training. The red points correspond to agents trained with L0 equal 1, while the blue points correspond to agents trained with L0 equal 8. As expected, the agents trained with a wider acceptable range, blue points, achieved higher diversity than those trained with a narrower range, red points. We trained 3 agents within a single model in our intrinsic methods and recorded their win rates during training. As a result, the win rates among the agents at the 800th age was similar for both black and white. This indicates that our intrinsic method successfully achieved quality across agents. Here is a summary of the experimental result. In the static method, our method nearly caught up with a supervised learning agent in error rating at 400th age, and our static method successfully focused on the intended zone. In intrinsic methods, in terms of quality, our methods show results comparable to the RL baseline in error rating, and all agents have a similar win rates for both black and white. In terms of diversity, wider acceptable range during training resulted in the higher diversity. Here is a summary of my presentation. The goal of this research is to make a Go AI agent which can propose multiple diverse strategies. To realize this idea, we tried 2 methods: static methods, which characterize each agent in which area the agent wants to secure, and second, intrinsic methods, which train agents using the intrinsic reward to promote playing diversity. As a result, in the static methods, our agent successfully focused on the intended zone. In the intrinsic methods, our agent achieved performance comparable to the normal RL agent in error rating, and we observed that a wider acceptable range during training led to higher diversity. I'd like to close my presentation here. Thank you very much for your attention. I would be happy to take any questions.
Okay. We thank for the presenter.
Yes.
So, is there anyone have any questions? Okay. So looks like currently no one has questions. So once again, I will ask a simple one. In the beginning, you said that the human would like to choose a AI agent which is suitable for him or for her. So, after you have successfully trained those agents, do you have any suggestion for the human player how to choose the suitable agent for them?
Uh, suspicion.
Uh, suggestion
Suspicion.
or advice for choosing the agent for the human player?
Uh, so, in Go, I don't know what to say in English, but there are moyoha and jitsuriha, which means people want to prioritize the center part of the Go board and edge of the Go board. So I think so
Oh, okay. So you means depending on the agent would occupy the center or occupy the edge or corner, we can select the corresponding agents, right?
yes. Uh,
Okay. Okay. It's quite a interesting thing because I think people all like to have a private coach to train them to have better skill on those games. Yeah. So I think it's going to be very useful in the game society.
Thank you.
So is there anyone has any other questions?
Uh,
Okay, so if there is no, then we thanks for your presentations.
I
And
sent you a
then,
question.
oh, okay,
And the
okay.
question is, you said at the end, I want to work with an AI that feels compatible with me. Yes? And my question is, and I looked also in what you think about the different strategies which are helpful for collaboration. What is your aim? What is what you're aiming at? When are you satisfied? Or when do you come to me and you say, now I have a fantastic result? And what then is the result?
uh, so 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 you so you um, uh so that's a question about the goal of this research.
Yes.
Uh, mm, uh, at this moment, uh I I cannot uh not draw the clear image of that, but ideally, ideally, mm, when do some enquetes, uh, and and
Let me help you a little bit, yes? your predecessors, they had in mind to solve a game or to bring a game to a higher level. Let's, for instance, they spoke about Othello, etc. You speak about, I would say, also diversity, yes? And you said, is an AI capable of presenting multiple strategies? Yes, and that could be, I would say, emphasis here, there, and everywhere. So, what is now the couple of, I would say, preferred entities you would like to have assembled for a good result?
Ah, mm, uh, uh, so, my, so uh, my emphasis on this research about my emphasis on research, right? So I emphasize. Uh, so at this moment, I prioritize make AIs match each person's preferences. Am I answering right?
But let's say you would like to make AI more clever, or you would like to make AI more friendly to you, more empathic to you.
I want to make more friendly, make more friendly AIs.
Okay, that's a good idea, and I wish you much success with your further research. Thank you.
Thank you.
Okay, we thank for Yap's very interesting questions. Okay, so once again, we thanks for the presenter, and we will go to the third presentations. So you can close your screen sharing right now. Thank you. And for the third presenter is the Tzu-Yang Xu. You can share your screen. Tzu-Yang, are you there?
Yes.
Okay, okay.
Is the screen visible?
Yeah, it's full screen right now, and we can also hear you. Okay. So
Thank
so the third presenter is Tzu-Yang Xu, and he's going to present his work entitled with Adapting MCTS algorithm for stochastic gain and example on EinStein Würfelt Nicht. Let's welcome the presenter.
Hello, everyone. My name is Tzu-Yang Xu from Institute of Information Science at Academia Sinica in Taiwan. The paper I'm going to present is Adapting MCTS algorithms for stochastic gains, an example on Einstein Würfelt Nicht. And here is the outline of my presentation. In this paper, we use Einstein Würfelt Nicht as an example to demonstrate how we adapt the MCTS algorithm for stochastic gains. And EWN is a stochastic game with a die roll in each play. Hence, the complexity of the game is greatly increased. And it seems that the gantry structure of stochastic game is more complex than that of deterministic game, which makes the MCTS algorithm converge much more slowly. And our modifications are mainly focused on the selection and the simulation stages to deal with the problem. First of all, I will briefly introduce the rules of EWN. And EWN is a two-player stochastic game with perfect information, and the board has a size of 5 by 5. One player holds red pieces starting from the top left of the board, and the other holds blue pieces starting from the bottom right of the board. Each side has 6 pieces numbered 1 to 6. And for the initial board configuration, one player can arrange his or her 6 pieces, and the other player must place the pieces with same number in the symmetrical positions. When the game starts, 2 players take turns to roll a die and make moves. The player must move the piece with the roll number if it is uncaptured. Otherwise, the player can choose an uncaptured piece whose number is either next higher or next lower to the roll number to move. And the selected piece can be moved 1 square horizontally, vertically, or diagonally toward the opposite corner. And for example, in this turn, if the red side rolls the number 4 and the red piece number 4 has been captured, the red side can choose either piece number 3 or 5 to move. And there are 2 winning conditions in EWN. One is to capture all the opponent's pieces, and the other is to move a piece to the opposite corner square. In this paper, we use Monte Carlo tree search as the main algorithm to determine the move with the highest win rate. And MCTS consists of 4 stages, including selection, expansion, simulation, and backpropagation. In stochastic games, we usually use chance nodes to represent the chance events during the gameplay. In our paper, we use counters to record the selected times of each chance node and select the chance node with the lowest counter value during the selection stage to maintain the uniform selection among dice outcomes. We prove a theorem that evenly distributed sampling times to a group of equal probability and equal variance events will obtain the minimal expected variance. Because of the chance nodes, the gantry structure becomes more complex, which slows down the convergence speed. In EWN, the gantry structure is one level of dice nodes followed by a level of move nodes. The dice nodes are chance nodes represent the dice outcome, and move nodes represent the legal moves based on the dice outcome. And each move node's 6 chance node children are simulated roughly an equal number of times. However, only one of the dice outcome will occur in the real gameplay. So move node has the statistical confidence of only 1/6 of its simulations. And as a result, the convergence speed of a move node may be overestimated. Accordingly, we define the effective visit count to reflect the probability weighted visit to move nodes chance outcomes. And equation 1 shows the calculation of the effective visit count of move node I. In this equation, Pik is the probability of each chance outcome occurring, and Vik is the visit count of the child k. And the effective visit count of I's parents is to sum over the effective visit counts of I's siblings. By using this effectivity counts, we can generalize the UCB formula for selecting the move node I as shown in equation 3. In this equation, the exploitation term is the expected win rate of I obtained from its chance node children, and we use the effectivity count of I and I's parents in the exploration term. With this method, we can avoid estimating the convergence speed of move nodes. During the selection, when the selected dice node corresponds to a character piece, we won't expand or simulate the move node of it to save the computational resources. Instead, we combine the moves of adjacent alive pieces into one virtual node and select the move with the highest UCB move value. For example, if the pieces 2, 3, and 5 are captured, and we select the dice node 5, then we will combine the moves of pieces 4 and 6 into one virtual node and select the move with the highest UCB move value directly. Similarly, when we are simulating the newly expanded nodes, we will reassign the simulations of the captured pieces to its adjacent neighbors. For example, suppose that we have total of n simulations, and we first run n over 6 simulations for the uncaptured pieces, not 1, 4, and 6. And then we reassign the simulations for the captured pieces 2 and 3 to pieces 1 and 4, and reassign the simulation of piece 5 to pieces 4 and 6. And we also prove a theorem that the modified algorithm will have the minimal variance among those independent pieces and minimal regret among those dependent pieces. And after the simulations are done, we calculate the weighted average win rate to assign the win rate for the capture pieces to improve sampling accuracy. For example, after the simulations, we can obtain the win rate of moving pieces 1, 4, and 6. And if the win rate of moving piece 4 is greater than that of pieces 1 and 6, so we will choose piece 4 to move if we roll the numbers 2, 3, and 5. So the weighted average win rate of node I is calculated like this. We also use other frequently used methods to improve sampling accuracy, including making the winning move directly or utilizing the eigenvalues values in simulations. And in our paper, we use up to 6-piece eigen database. Next, in our experiments, we compare the performance of our improved agents with the baseline, and the baseline program expands and simulates all possible move nodes for each dice node. And all of our experiments were done on a computer with the specifications listed on the table. In these experiments, we compare our improved agent against a baseline with varying numbers of pieces and numbers of iterations of MCTS. In these diagrams, the x-axis represent we use T-piece n-GAN database in simulations, and the y-axis represent the win rate from the perspective of our improved agent, and different line colors represent the different iterations. In these diagrams, we can see that the improved agent can achieve a higher win rate when the number of iterations is small. So showing that the improved agent converges significantly faster than the baseline. And in these experiments, the improved agents play against the baseline with using T-piece n-GAN database in simulations. In this diagram, the x-axis represent the different version of the baseline program, and y-axis represent the win rate from the perspective of our improved agent. And different line colors represent the different versions of our improved agent. In this diagram, we can find that the version B0 also outperformed the version A6, and showing that our improvements provide greater benefits than simply utilizing 6-piece n-GAN database in the baseline simulations. And finally, the conclusion and the main contributions of our paper is that we propose an adapting MCTS algorithm that better accommodates the characteristics of stochastic games. And the experimental results show that our improved agent converges much faster than the baseline program, showing that our modifications are effective in speeding up the convergence speed of the algorithm. And this is the end of my presentation. Thank you for listening.
Okay, thanks for the presenter. And if there's anyone has any question. Okay, so looks like currently there's no question. So once again, I will ask a simple one. As we know, the EW again is basically with uniform probability. So do you think this approach or this algorithm can apply to some gain with some non-uniform events? For example, the probability distribution is non-uniform.
For this question, I can use the effective Vidicons to explain. For the games with non-uniform chance events, such as we flip unrevealed piece in Chinese stock chess, we just need to replace the probability term Pik in this equation with the actual probability of each chance outcome when we calculating the effectivity counts. So this method, I think, it also applies to the games with non-uniform chance events.
Okay, let's think. We will more like more general methods, and maybe we can try to apply it to some of the other stochastic gain to see the corresponding result. Okay. Is there anyone has any questions?
Now, maybe one question on the effective visit counts. Yes.
Yes. Okay.
That is the most, now for me at least, the most interesting point of your whole presentation, because when is it effective? And that is quite. How do you handle that? How do you explain that? You give formulas, and I understand the formulas. I understand also what is a winning position. But now I'm sitting at home and I can follow the formulas. And then I would say, could you indeed give me some feeling of what is effective, how I can see as human what I should play? Or do you tell me, listen, this is not a game for human against human or whatever. This is a game only for computers.
We use this formula to calculate the effective basic count is to avoid overestimating the convergence speed of move nodes, because we evenly simulate all chance outcomes under move nodes, but only one of the chance outcome will occur in the real gameplay. So we use this formula to avoid overestimating the convergence speed of the move nodes.
Yes, I understand what you try to communicate with the user and also with the program, of course, that you have I would say, a weight or I would say a good decision, yes. But if you now would like to teach the human being to make good decisions, what is then the I would say the hands-on you give him apart from all the formula? Because the formula, he can use the formula for a computer, but not for his own mind.
So I think Yap's question is about if a human player
Yes.
want to apply the same strategy you're talking right now, how can we apply the same strategy? Maybe according to your formula or do something else.
Thank you. That is exactly what I would say, yes. So thank you for the improvement.
For this question, in my experiments when I'm playing these games, I think I won't think so much about how to use the formula when I'm actually playing this game. So.
Let me give you one thing. Assume I'm not a chess player, and a little bit I know how the pieces are going, yes. And then I met for one time I met Botvinnik or Karpov, or I met the current world champion, and he tells me a little bit about why he opens with e4 and what is then important. So you could say we should use the development of the pieces, strong fields, and have power in the center of the board. Now that are some guidelines. And now my question is, what is an effective visit? What is so that you have an effective move? I know that the rule is, of course, that you go to the other side, for instance, in the corner. That is, I would say, what you could do. So I understand that if I'm almost there, that you should say, push that stone forward. That is quite clear. But if it is not a matter of pushing the stone forward, then I have to develop a strategy. And you come up with a strategy which is, I would say, difficult to express in another terminology than, I would say, the computation of chances and weights.
I think from this formula, maybe at least we can learn from the thing we can learn from this formula is it's a expectation. So maybe we should pay more attention to the one with higher probability. Maybe. What do you think about this kind of strategy?
I fully agree with you because you now try to convince me that I would say the computations are fine, and I would say the effectiveness is also fine, yes. And the way we compute that is also fine, so that I agree. But nevertheless, then I said that if I see the outcome, yes, and how do you, I would say, then convince your human spectator that that is the best move? I think this is a question for, I'll say, the next conference, because next conference is in Maastricht, and I wholeheartedly invite you to come up with, I would say, a first answer to this question, because I'm convinced that is a very difficult question, and it is, I would say, it is almost at the core of the business, or just not at the core of the business, you could say, because our business is mathematical computation and then evaluating it with chances and with probabilities, and not, I would say, with explanations. But so you see now here why it is in artificial intelligence, explainability is one of the most difficult branches. And in fact, my question was a question on asking for the explainability of your outcome.
Okay. So we hope we will see you next year in Netherlands, and you
Yes.
can provide us answer to the current question.
Okay, now that's a challenge up to me. I understand. I can only repeat that current question that I would say. Yes. Thank you, thank you. You did a good job. So my compliments for everything what you explained to me, because your talk was, for me, it was a good to follow talk. It was nice one, nice to listen, and nice to see what progress you made in your country. Yes, and give greetings to your teammates, of whom I know 3 of them very well. Yes, thank you.
Thank you.
We thanks for your questions, and we thanks for the presenter. Okay, so we are going to today's last presentation, which is presented by Taylor Neller. So Taylor, okay, you can share in your screen, and you should open your mic.
Yeah, I'm just setting everything up. Can you
Yes.
see me all right?
Yeah, we can see your slide without any
All right.
problem, and then also we can hear you clearly. So,
Awesome.
so the next presenter is Taylor Neller, and he's going to present his work entitled with Evolutionary Tree Search for Turn-Based Strategy Gains Taylor, please start your presentation.
All right, thank you. I'm Taylor. I'll be presenting evolutionary tree search for turn-based strategy games. This research was done as part of my master's thesis at Virginia Tech. So the research focus of this research is multi-action turn-based strategy games. So these would differ from conventional turn-based strategy games like chess by requiring multiple moves per turn. So think chess, but instead of one piece, you're moving like multiple of your pieces per turn, or all of them. On the right here, we have an example of a turn-based strategy game, Advanced Wars, which is one of my personal favorites. And you're going to be moving a lot of these different pieces on your turn. Like each piece can take like one move per turn. And so there is a huge branching factor to these types of games, far more legal actions per game state than usually there might be in a board game. And also there's another challenge in this line of work is that there aren't the same sorts of focal games like chess or Go that draw a lot of research attention. So there are less papers to compare against. And there's also a variety of games that people are doing research on and not just a few. So our research goal here is to improve upon state-of-the-art turn-based strategy search frameworks, most notably Monte Carlo tree search and Rolling Horizon evolutionary algorithm. We choose a simplified version of Advanced Wars called TubStab, which is a game framework made by Fujiki et al. In 2015. This game has two teams, red and blue. Each turn, all of the units move once. There are 6 unit types. HP ranges from values 1 to 10 in the upper right corner of each unit here. And there are 5 terrain types that units traverse. We chose this game not only because it's fun, but also it's representative of turn-based strategy, and also there's a body of work to accompany it as well. The game ends once one side is annihilated or 30 turns elapse. After 30 turns, if neither side has more than 10 HP than the other side, the game is considered drawn. So, as you are well aware, Monte Carlo tree search is a very common technique used for game tree search. But another very popular algorithm to use as a foundation in these sorts of agents is called Rolling Horizon Evolutionary Algorithm, or RHEA for short. And in this algorithm, instead of doing any type of tree search, you have a population of action sequences that you evolve. So on the right here, we have an example of a tic-tac-toe game tree with a root state, and we're going to compare it to RHEA. So in RHEA, you instead have a population of H-length action sequences, where H is the horizon length, and then you use mutation and crossover operations to generally get a better and better population of action sequences. So to give a visual example here on the right, we have a root node up top, and then we have 3 action sequences with horizon 2 for 2 current player moves. The current player is O here. The Rolling Horizon Evolutionary Algorithm was originally developed for the traveling salesman problem, a real-time variance. And so it's made for single player, which means that for any sort of adversarial adaptation, you're going to need to have some sort of simple player for the opponent to model the opponent's actions. So if we were to look at one of these action sequences, we can see that O makes one move, then we have to model X's move based on the state previously, and then we have another move for O. And then what we're going to do is we're going to apply modifications to these X moves to change the action sequences over time and get better ones. And we'll explain exactly kind of like what these mutation and crossover operations look like for the TubStab domain later in the presentation. So we implement a few baseline agents for our analysis. MUCT is a state-of-the-art Monte Carlo tree search implementation for TubStab by Muto and Nishino. And then we make a modification to it, adding progressive widening for one we call MUCTP. We also implement RIA, and then we also implement a hybrid algorithm, evolutionary Monte Carlo tree search. And this instead applies Monte Carlo tree search to the genetic space of current turn moves, so action sequences for the current turn. They also have an extended version of this, which searches over longer horizons with multiple turns instead. We also have a simple rule-based player as well. So when we are comparing our baseline agents against each other, we note that Monte Carlo tree search performs poorly against RIA in complicated action spaces, and the reverse happens in small action spaces. This is a pretty widely observed trend. We know that Monte Carlo tree search is good for games, especially as the branching factor is smaller. And then RIA was determined for developed for real time, which is a very large action space because it has to happen very fast. We design turn-based evolutionary tree search, or TBETS for short, as a hybrid algorithm. And the key modifications here are that we change the tree structure and we use evolutionary algorithm-inspired operations in the expansion phase of Monte Carlo tree search. So for the tree structure, we want to traverse only the turn start states instead of every possible state within a turn. And this has the effect of compressing the game tree vertically and vastly increasing the branching factor. And so branches to children would represent sequences of actions as opposed to singular actions. So the core idea here is that we have an initial state here, and we only want to have children that are after the entire turn is done, not just one action. So we see here in the middle, one action might be a singular tank move and attack there, whereas one turn would be every unit moving. So we're going to walk through the 4 stages of Monte Carlo tree search here, starting with selection. For our little diagram here, each node has 4 little symbols, and each of those symbols represents an action. So each of these nodes here is actually representative of the branch it took to get to that node for individual actions for 4 units. So in the selection phase, we use the UCT algorithm, just like MUCT, and we also modify it so that it can select leaf nodes as well. So any node in our tree can be selected, and we use UCT. For the expansion phase, if we select a node that has children, we apply evolutionary operators with a fixed probability. So for the mutation operation, this is selecting one child of the selected node, and then we apply a mutation to it. So what we do is we have a percentage chance that the actions in the sequence will be modified, and then we create this modified action sequence, repair it if necessary, and then make it into a new child of the selected node. Similarly, we can do the same thing with crossover, except that we take 2 children of the selected node, and then we sort of splice them together. We take a few actions from each of the action sequences of the 2 children, and then put them together into a new one. And then we attach this new child to the selected node. If a node is selected in the selection phase that has no children, we instead generate some initial population, which we set as 5 random children. For the simulation phase, any child that is generated will have a depth 2 playout from it, evaluated by a simple heuristic, and this simulation is conducted with the simple rule-based player. Backpropagation is exactly the same as in regular Monte Carlo tree search, updating the visit count and the node value all the way back to the root. So here we have a summary of comparison of T-bets versus both of its derivative algorithms. We try to keep things pretty much exactly the same as much as possible. So we keep the same mutation and crossover, tournament selection, random move selection, and opponent simulation as the RIA algorithm. And then in Monte Carlo tree search, we try to keep everything the same except for expansion, which uses the evolutionary algorithm operations, and simulation due to the changes in the tree structure that necessitate a different type of simulation. And so we try to keep T-bets the same as both of these in order to compare them more effectively. So for our evaluations, the way we decided to perform is to have a bunch of head-to-head matchups between each of these agents over a variety of maps. We have 5 different map types, each with a set of 100 random maps ranging from 3 units on each side to 10 units on each side. We keep the time control constant, giving each agent 100 milliseconds of thinking time per turn, and instead vary the map sets to gauge how well these agents do on different complexities of maps. For our 3-unit map, we have 2 infantry and 1 tank per side on a 6x6 planes-only map. The 4-unit map is an 8x8 map with randomized terrain and 4 different units per side. The 6-unit map is an 8x8 map, and we try to skew both sides towards opposite corners in order to make the starting states fairer. And then we have an 8-unit 10x10 map and a 10-unit 12x12 map as well. So here's our first win rate table here on the 3-unit map. We code the cells in green if that head-to-head matchup is a win, and red if that head-to-head matchup is a loss. Next to the win rate values in percent, we have a confidence interval, a 95% Wilson confidence interval. And we count here the number of matchups that are won, since there seems to be a rock, paper, scissors relationship between some of these top contenders. So overall, the Monte Carlo tree search algorithms come out on top in the smallest map, winning 4 out of the 5 matchups. T-bets and RIA both win 3, and then the other 2 algorithms perform very poorly. On the 4-unit maps, now T-bets is the dominant agent, winning all of its matchups, and then we have a pretty linear pattern when M is TP winning 4, RIA winning 3, etc. The key takeaway here is that MECT performs worse, and then T-bets and RIA both increase in their performance relative to their players. For the 6-unit maps, we omit the other 2 poor performing agents. We can see here that T-bets and RIA perform about comparably to each other, with T-bets having a slight edge. Notably, the Monte Carlo tree search algorithms fall off quite hard here, performing very poorly. This trend continues on the 8-unit maps, with the Monte Carlo tree search algorithms performing even worse. T-bets notably gains a decisive lead over RIA here, and as we look at the 10-unit maps, T-bets widens that lead even further to a 20 percentage point difference. And I forgot to explain, but these don't add up to 100 if you add across the diagonal, because there are draws as well. If we graph these trends over time, we see that T-bet starts worse than Monte Carlo tree search, but gets better over time. T-bets is consistently better than RIA, but especially as the games get more complex, it gets better. So our conclusions: T-bets overall performs the strongest of these agents, especially on more complex maps. RIA performs better as well as the map complexity increases, and then the other 2 agents perform very poorly. Our findings show that T-bets is an effective hybrid overall performing better than both as the game complexity increases, which is really good because most turn-based strategy games are even more complex than what we looked at here. So I'll skim through this for lack of time, but we have only a few baselines that we test, limited modifications to time control, and also for future work, we want to modify the baselines more and then apply those modifications to t-bets as well, since it's a hybrid algorithm that can sort of be the best of both worlds and take modifications that both of the others can as well. All right, thank you. Any questions?
Okay, we thanks for the presenter. So it's quite early in the US, right? Right now?
Right now it's 10 o'clock for me.
Okay, 10 o'clock is okay. Okay.
Not bad.
Okay, so if anyone has any question for this topic, okay, so
If nobody
currently,
has one question, I have one. And
okay, yeah.
that is the question. I see that MCTS is doing poorly, yes? And that is the result, so that's fantastic. And I followed all the things. Yes, you said it already, but often Tibet's outperforms both agents. And why is that the case?
Yeah, so we actually see that the Monte Carlo tree search performs better than T-bets on the small maps, and you would kind of expect that because like as the games get closer to like chess and other games that we know with limited branching factors and like less complex states, we know that Monte Carlo tree search is good. So the advantage that T-bets has is that it basically shares a lot of the qualities that RIA does, which allows it to very effectively find good moves in a short sort of horizon window. So like short look ahead, evolutionary sort of mutations are able to selectively find like needles in a haystack better than Monte Carlo tree search can. So that's why T-bets is able to beat out Monte Carlo tree search in more complex maps. Does that answer the question?
Yes and no. First of all, yes, it is absolutely convincing, and I agree with you because I saw it also in that way. But what this not answered my question is why is this the case? Because if there are apparently too many variables, yeah, then MCTS performance lowers. Is that true or not? That would be my conclusion. But you could say immediately that I'm wrong, but I try to have with the open eye of a spectator here and an interested follower of your lecture. And thank you very much. You did a very good job. You explained it quite well. But then you always try to find one step deeper. What is behind it? And so I could not find for myself what was now behind the better performances of the T-bets in relation to the MCTS performances.
Yeah, so I think it is best to compare RIA versus MCTS first. RIA tends to beat out MCTS as the branching factor increases and the game states get more complex. And that's because, in my opinion, or from what I've seen, it's just a more effective way to find good moves quickly, like it converges faster, whereas Monte Carlo tree search could perhaps find like the optimal solution given enough time. Evolutionary mutation and crossover is a more sort of the quicker convergence to a good solution. And this could be because with the Monte Carlo tree search that I have here, it doesn't have like a very advanced sort of move ordering sort of function.
Okay.
So like maybe perhaps if you put a lot of work into making like better move ordering, you could converge to a better solution quicker. But I think just like evolutionary mutation is very fast, especially since we're looking particularly at moves that the opponent cannot affect. Because Monte Carlo research is really good at adversarial modeling, like you can model what the opponent does just as well as what you can. But with RIA, you get significant improvements in looking at only moves that you can do because it doesn't like it's not like the opponent can try to throw a wrench in your plans per se. Does that make sense?
Yes, it certainly makes sense because you could say also that as the complexity of the area which you're in is moving to, I would say, real world areas which are even more complex, then it is, I would say, to be expected that artificial intelligence is worse performing in the real world area than in the game area. Yes,
Is that a question?
I see, yes. Now, it's not a question, it is a statement, but the statement and a question. And the question is, am I true or is there something wrong in my arguments?
About like AI being stronger in games versus real scenarios?
Yes, yes.
Hard to say because like we can say that AI is like demonstrably better at chess than humans are, but
Yeah,
also
but that's a simple scenario, in fact. That is not, I would say, the real world is a complex scenario. And chess is bound to rules. And the real world is not bound to rules.
yeah, I mean, I'd say it depends heavily on like the type of AI that we're looking at because like I mean, even for these turn-based strategy games, you can say that the AI is poor, like it performs far worse than humans do. Um, but like if we're comparing like sort of game AI, or if we're comparing sort of like LLMs and sort of general intelligence, it's two completely different things. So I guess I would need a better example of what you mean by like real worlds.
Okay. At least I find that very interesting. So that is certainly, and you brought it very well and very convincingly. So my compliments.
Thank you.
Okay, please. Thanks for your questions. And okay, looks like there's no further more questions. And I think we will end today's session here.
Thanks for chairing this session. Thanks to all the speakers of this fourth session.